Okay, thanks a lot. Many thanks for organizers to give me the opportunity to speak here and talk about analysis of models in the sense of Chris alluded to at the end of his talk. So what structural identifiability is about. So let's say we have a dynamical model, ODE model, very simple. This will be my favorite model for today. It's just two equations. They model flow of the material from one compartment to another. And there are two scalar parameters. I have time series data for x1, and I want to fit my parameters, okay, from this data. Now, well, this is a heat map. So I take different values of a and b and plot the log of error. And you see there a black dot, which is like a perfect fit. And I mean, one natural desire is just to take this point and go ahead. But if you zoom out, oops, there is another point, okay, which fits as perfectly as the first one. And that is the problem which we call lack of structural identifiability. So the model itself has certain symmetry inside, which prevents you from faithfully infer the parameter values, okay? Note that there is no obvious symmetry with respect to A and B in the equations, but there is symmetry if you try to fit. And StructuralIdentifiability.jl well, helps you to detect this issue, analyze it, and hopefully fix in some cases. So, and let me just walk through the main functionality using this model as my running example. So this is the same differential equations, but for data, I will now take not x1, but x1 scaled by also unknown parameter c. Okay, so first we want to define the model, and we have a macro for this, which, well, basically you write the model as it is, or you can write this in modeling toolkit notation, because then you can use the same model to fit parameters or to simulate them. And finally, if you work with chemical reaction networks, you don't need to write any equations, any differential equations at all, thanks to Torkel Lohmann. You can just use catalyst.gl. Now we have the model, what we can do. So we can ask the package to assess identifiability. There are two different ways of doing this. One is assessment of local identifiability. This is the fastest thing you can do, it's pretty fast, but it detects only infinite ambiguities. So it detects if parameter has infinitely many possible values. So here it says that A and B are clear, and C, x1 and x2 are not so good. And the plots, they sort of illustrate this. For the same y, you get a bunch of different trajectories of x2 if you just change c. So basically you can take any c and get a perfect fit. So that's why c, x1, and x2 are marked as bad guys. And a and b so far look innocent, but we know that they are not. Okay, we know that there are problem with them, but this fast analysis doesn't see this. We have slower analysis, which actually shows that A and B are locally identifiable. So there is ambiguity, but it's finite. Okay, there are finitely many problematic values. And now we get a more detailed picture. So now we can spot identifiability problem, but to reason about it, I still have to refer to pictures, okay? So now in higher dimensions, pictures are not as available. What can we do? We can try to get the functions which are actually identifiable, and the package can get you a complete set of quantities which can be uniquely identified. In this case, this is the complete set in the sense that any other can be expressed for them of quantities which can be identified, okay? And from this complete set, from the first two, you can observe this A-B symmetry, right? Because A times B and A plus B symmetric functions in A and B. And the second two, from them, you can also see the scaling behavior with respect to the constant C, okay? So now I don't need plots. I can now look at these functions and understand the things which we before understood looking at the plots. And that's much better than if you don't have, if you have high dimensions and you don't have access to good pictures. Now we know that we have a problem, okay? We have a model which is not identifiable. There are two issues. There is symmetry swap and there is a scaling. What can we do? We can try to reparameterize it. So we have function reparameterize global, which takes your original model as input, and then it produces two pieces of information. The first piece of information are new coordinates, and there is no coincidence they have the same functions which you have seen on the previous slide. So basically it tells that you can use these functions as new coordinates, and in new coordinates it writes a new model, okay? From the point of view of numerical behavior, it's equivalent model. But now it resolves ambiguities. So this new model, first of all, it has few parameters in the sense that there is no C, right? It's just A1, A2. And thanks to that, it's globally identifiable. So all these quantities, A1, A2, X1, and X2, they can all be uniquely inferred from the data. Okay, so we resolve ambiguities and we compress the model, which is nice. So that's how this analysis works. So you start with a model, you can spot identifiability problem. You can get a finer description to understand what was the exact issue, what was the exact cause of the problem. And finally, you can use this finer analysis to get a new model, which is hopefully better suited for your purposes. So here I'll finish this. So as I said, SIGL can help you to with your OD models, but in fact we can do a bit more. We have also discrete time models, and we're allowed to provide some additional knowledge about the model, in particular known initial conditions, but there are some limitations here. And yeah, if you have your model and you would like to maybe look at this, I'll be happy to do that. And of course, if you're interested in this sort of analysis and you have some feature requests, I'm happy to discuss as well. And I would like to finish by thanking all the contributors to the package, notably two student contributors, Ruven Donk and Alexander Jamin, who Ruven was co-author of the very first version of the package, and Alexander was a driving force behind the recent developments. And thank you very much for your attention.
Thank you very much.
Hi, thanks for the nice talk. But how good does it scale? So, okay, for 4 variables, finding 3 identification function is good enough, but if I have 1,000 variables, how would it turn out?
Okay, so 1,000, I mean, local you can still do, I think. Well, it sort of depends on how badly nonlinear equations are. For finer analysis, that's a big problem. So it doesn't scale, well, the algorithms behind are sort of exponential. It still depends on the type of nonlinearities. So if you have very few nonlinearities, you can be still good. If you have a bunch of Michaelis-Menten things, that will blow up pretty quickly.
Okay, I see. Thanks.
Do you have false negatives in the slower method?
Okay, that's a good question. So the algorithms, theoretically, they allow false negatives in principle because there's some randomization behind, but there is user-specified probability. You can set the probability of false negative to be less than 1,000 of 1%. But apart from that, no. So for the speed, you pay with the quality of the result, not with the correctness, not by the correctness.
Thank you.
Thank you. In optimal control, we can have like 2 ODs with the same shared parameters. Is it possible to fit the parameters of 2 ODs?
Well, I mean, one obvious solution is just to put them as a single ODE system. Isn't that a problem? Like, not feasible in your context?
Yeah, it may be.
Of course, I mean, another option is you can first get identifiable functions for one of them and then use them as a side knowledge for the other one. That would allow you to basically balance the workload.
Yeah, okay.
But that's interesting. I would look at this.
Thank you.
Thank you. It's okay. Thank you very much.